couple seconds. Okay, I think we're live.
Okay, nice. Okay, let me just start. Hi everyone, my name is Danny. I'm currently AI resident. I'm an AI based in Melon Park. So today I'll be doing a brief sharing on the on-device ML and efficient model training. So keep in mind that this sharing will not go too deep into technical detail because time is constrained. So this is more on the introduction on how on-device ML works and how do we do efficient model training generally in the industry and what are the latest research breakthroughs. So here are the agenda for today. So first I'm going to go through what is on-device ML, and then I will go to all the different methods we're going to use, or the most popular ones we use for efficient model training and inference. And then I'm going to share some learning resources, more like introduction materials for anyone who's interested, like how do you get into on-device ML and how do you learn more about different parts of on-device ML. Right. So let's start with some really nice examples to get a hand of what is on-device ML. So on-device ML is very general terms. It's not just for one really specific areas. So if you're interested in computer vision, if you're interested in like speech recognition or NLP, they are all possible examples of on-device ML. So the first one is TikTok boat filter. So people know that we have been using filters on different apps like Snapchat or Instagram for a very long time. But the thing is, most filters in the past are not really designed to be filtered to your facial structure because everyone's facial structure is very different. But so if you're using some older filters, it's actually just a kind of like a mask snap on your face. But if you're going to use very specific better facial tones, it's going to be using facial recognition, and that's really specific design to your own face. So we can say we have a survey model that's used to detect your eyes, your nose, your like all the facial structures, your hair colors, and then we can do some facial tones. And for that to work, it's actually just a really lightweight on-device ML model, generally a facial recognition model. And the reason we say it's on device because the model runs on your mobile device. It's not on the cloud, it's on your mobile device. It's like integrated as a part of the app. And it's very lightweight because we can just using the computing resources of your mobile phone to do the inference. And because model is already trained, so that's what we say on-device ML. So generally for on-device ML, model is already trained, but we need to do the inference on local devices.
Right. So just stepping back a little bit. So today's session is going to be about on-device ML and how do you build efficient ML models that can be run on device, right? And Danny's here to help us walk through the process and help us understand her research on this in this area. So Danny, you just to quickly summarize what you're mentioning is that we have a lot of real world use cases today on different apps where we need to do on-device ML, where the model is actually trained in the cloud, and then it's on the device, and the inference runs on the device whenever on request or in background or based on whatever the use case is, it would be running on the device. And when you say run on the device, it's basically getting inferences on the device, right?
Yes,
the model is not training on the device; it's training in the cloud somewhere.
Yes, exactly.
And getting deployed. Thank you.
Perfect. Right. So that's for the first example. And we can say like the effect is getting better and better. It's more tuned to your own facial structure. And some people are getting kind of a little scared. So that's how good some city models getting for their facial structure. And the next one is also really popular one this year. It's a AI chatbot, like my AI chatbot released by Snapchat. So it's different. So this one is different. It's not a Siri model. It's an NLP model. Basically, it's going to process your words in the real time and do some lightweight conversations. And this is also like on device because it's also running like it's integrated in a Snapchat. You're doing the real time processing of like NLP. So and if you go online, you can search some really fun examples of Snapchat conversations. So the next one is Alexa. So this is also really popular. And I said it here because it's different than the previous two. The previous two, first one is CV model, the second one is NLP model, but for this one is an ESR model. For Alexa, it's just running your Alexa devices. And from all the three examples we have seen so far, we can see actually that apart from running inference on device, all the on-device ML models, they share the similar characteristics, which is they're more secure, because when we do the inference on device, we don't have to upload your user data to the cloud. We don't have to upload it anywhere. So we retain all those information on the local devices, which is one of the reasons people are really interested in doing on-device ML, because it's more secure and data, you don't have to share your personal data anywhere. And let's see some more interesting examples. So for this one is TensorFire. TensorFire seems a little bit complicated, but it's actually just a ML running in your browser. So in this case, the device is actually on your laptop and the running interface is just your web browser. For example, this one, TensorFire, it's a CV model that, or like a video recognition model that can recognize your all your hand gestures, and we can do like rock, paper, scissors in real time. And
that's fun.
Yeah, this is really interesting. I think this was also released like recent years. It's a joint collaboration, I think, between MIT and I might be wrong here. I think it's MIT between another company with, I think it's Google, but I'm not so sure. I need to double check. So I added the link for you to check this. This is their official website. And yeah, and here are some also really interesting examples. So for smartwatches, we do not just have Apple Watch, but this is one of the most popular ones. We all know that if you're like talking to your smartwatches, like say Siri set an alarm in 15 minutes, it will work. So for that one, it's ASR model, but we have also some like other really interesting ones. For example, this is a health feature that Apple released in the past few years, and it basically will just monitor your heart or like all your health activities and give you maybe some notification if you encounter some events. So this one is also one of the many examples that are like ML running on device, because it can detect and it can do the prediction based on the information you have. And when we do that, it does not upload any user information on the cloud or like to remote servers. So it's more secure.
Interesting.
Yeah. So now let's just take a step back and see like what kind of devices are we talking about? So when people say like when we're talking about on device, we generally see like we're talking about mobile devices or smartwatches, but it's actually much more than that. It's not just the watches and mobile phones. Basically, any smart devices nowadays, it can be a device for on-device ML, as long as we have the computing resources. So of course, we have the mobile devices, mobile phones, and the smartwatches, and the laptops. Those are the most popular ones that came into man. But then we also have automobiles. For example, if you guys live, I think you all live in the Bay Area, so you can say if you go to the city, like you can see Waymo and Cruise, they're doing some self-driving car test. So basically, when those cars are running around, they're roaming the city, they need some sort of technology to identify where they are and how do they make the turn. Like, are we stopping here because they're passengers, or we can just go because it's a green light? And we know that there are some cameras like integrated in the automobiles. For example, we have the radar cameras, and we can do some recognition. And those recognition is just the real-time video processing or real-time image processing of some sort of image recognition model, or just generally recognition model. And those models, we know that they need to run in real time. So that's one of the examples, which is automobiles, which is kind of different than the phones and smartwatches, but still it's considered like devices. And then we'll have a very large collection of smart home devices. We have Alexa, Google Home, or your touch screen. Those are all part of devices. And then we have laptops. And there are many, many more. So as long as it's a technology gadgets, or it has some sort of computing resources, computing power. Like for example, it has storage, it has memory, it can be connected to the internet or something similar. Even though connection to the internet is not a must, because we know that one of the major concerns of on-device ML is security. So sometimes we don't have to connect to internet because we don't need to upload anything. We don't need to connect anything. But yeah, so that's a general devices. It's a very, very large collection. So which is one of the reasons I'm not going to go too much detail. So I'm also going to talk about the very general terms of what they are and what they do and what are the latest trend. Right, now let's see, now that we know what devices are, let's see why do we need on-device ML. So the general goal is we are not going to perform the inference of the models on cloud, because we know that the standard process of an ML model is we train the model and then we do the inference. And then when we do the inference, we use the user data, or we use some very specific data that we collected, and we try to get some really nice results. And for training, sometimes data is not really related to yourself. It's sometimes we collect it from elsewhere, like we use some open source data set, we use some data production data set. It doesn't really matter. So what matters is how do we do the inference. And the goal of on-device ML is just we're going to perform inference with models directly on device. And why do we do that? So there are multiple advantages. If you go online, you can search. There are many popular blogs. You can say like go into details. They're going to tell you why it's that. So I'm just going to highlight a few like really popular ones here. So first one is the low latency. Why there's low latency? Because we don't need to upload anything to the cloud, because generally, like if you're using AWS or using Google Cloud, you need to first upload some local like user data or local parameters or model weights to the remote server, and then we download it back. And that is largely constrained by the bandwidth of your internet or your connection that day. So there's a lot of factors we need to consider into it. But if you're doing on-device inference, that means we can do all on your local devices. We don't need to rely on the internet to do the inference, which means we have very low latency compared to remote server, like cloud-based models. That's one of the major factors. And the second one is privacy. So like I have mentioned this before, because on-device ML is very secure. We don't have to upload anything. We do it all on your local devices. And if user is placed, they can just delete the model, or they can just delete the app, and that was it. So that's a privacy concern. And the third one is also similar to that one. It's the previous one is just offline work mode. We don't have to connect to the internet, even though you have the option for the most models you have. And the first one, I think, is more related to developers, because there's no cloud bills, because we all know it can be very, very expensive, especially for like AWS or Google Cloud.
Yes, moving the data is expensive. Yes,
very, very expensive. Which is one of the reasons like not a lot of smaller companies are doing, they're not doing like very large scale cloud computing based, like cloud-based model training, because we know like if you buy like large group GPU, it's going to cost a lot of money. So that's for the pros. And for the disadvantages, we also have a few, but it's all well concerned. The first one is we have very limited computing resources. So we know that why do we use cloud? Because cloud has most computing resources, computing powers that our local devices doesn't have. For example, when you train a model, you don't train on your local, like whatever your MacBook or your Linux or Windows desktop. You do it in the cloud because you SSH to a remote server and you do the computing there. Why is that? Because our computer has very limited computing resources. Limited as in it's not as good as cloud-based servers are, which means if you are going to do some inference, it might be slower if compared to the cloud-based models. And the second one is memory. And I'm just going to take two of these together. So memory and storage, of course, because it's mobile gadgets. For example, your cell phone, your smartwatches. So people design it to be lightweight and can be used like in daily tasks. So those two are definitely not as good as like cloud-based servers or computing resources. And the last one is power consumption. So this one, I think is easy to deduce. For example, if you run a lot of things at the same time, for example, in your MacBook, then it's gonna take shorter amount of time for your computer needing to be plugged into like a outlets and starting to get powering. So that's for the power consumption. That's the general background of on-device ML. So far we talked about the goal and the pros and cons. And now let's go to the second part. Sorry, let me see the chat.
That's okay. I'll keep an eye on the chat.
Okay, nice.
Yeah.
Thank you. So the second part is we're going to go into details of how do we do efficient model training and inference. So I'm going to preface here that it's not generally like constrained to on-device ML, even though they're much related. So things we mentioned here, for example, like quantization, neural architecture search, or pruning distillation, it can be applied elsewhere. So it's not just like really just related to on-device ML, even though there are some like really popular techniques we use in daily tasks. So right, so why do we do like efficient model training and inference? It's a very general terms in ML research and production. So, but the general goal is we're going to try to make lightweight ML models. Why we have to make it lightweight? We need to make it able to run on local devices, because as mentioned before, we have many computing resources constraint, memory constraint, storage constraint, power constraint. So we need it to be lightweight. But at the same time, we don't want it to lose too much of its performance, because we know if you make it smaller, the smaller model generally, like smaller the model are, they are generally like less efficient or less performing as well compared to the larger models. So some techniques I'm going to mention today, we have quantization, pruning, distillation, and then as neural architecture search, even though there are many, many more. So first one is quantization. Quantization, it's a process of mapping continuous infinite values to a set of discrete finite values. So the goal of doing quantization is we're going to reduce the computing and memory costs by presenting the weight activations with low precision data types like 8-bit instead of general like float32. If you're going to a lot of packages and tools in ML, for example, if you're using TensorFlow or using PyTorch or JX, generally those type of tools are already implemented. And even though they are not, you can do it yourself. But the general goals is quantization is somewhat is very specific to your models. So you have to maybe do some kind of customization based on how your model is designed. But generally, it's very easy to do. And the second one is pruning. Pruning, as the name suggests, is already pretty obvious. It's a very popular data compression technique that reduces the size of the decision by removing a section of the tree that are not critical or redundant. And pruning in ML is a practice of removing parameters. So it's almost similar to the previous one. So we remove some individual parameters or in the groups that from an existing network, so that it's faster to do the inference in the next iteration for one network. And next one is distillation. So I think a lot of people have heard of like knowledge distillation as one subsection of ML research, but distillation here refers to more broader terms, which is also like we have data set pruning, data set distillation. So for knowledge distillation, we have it's a predictions of large, more complex teacher models, which can be distilled into smaller models. And then we have data set distillation algorithms, which is used to optimize data set using loss function from kernel regression. So this one is one of the latest research, I think it's from ICLR 2021. It's pretty new, but we can use it to distill the data set we use. We can use it for training or we can use for inference. And the next one is neural architecture search. So I'm going to spend more time here because it's a very interesting technique. It's actually pretty old. Like it has been around since 1980s, but it doesn't really gain popularity until recent years because there's a boom of NAS or neural architecture search. So what is neural architecture search? It's a technique for automating the design of the artificial neural networks for a given task. And we need to emphasize on a given task, because the general NAS so far is not very general, or it cannot be cannot be used for multiple tasks at the same time. We have to design it specifically for a very given task. And the task here we refer to are computer vision, natural language understanding, speech recognition. And sorry, I put it here. I think it's reinforcement learning. So basically, NAS is basically, it's a method, or it's a technique that we use to do one of the task understanding, and it can be applied to multiple areas. But the thing is, we have to design it very specifically for a given task. So here it's just one of the many examples of how do we design the NAS architecture, but it can be specific to your own model. So here's another example, but the general term is, the general rule is, we need to design the search space, which is the most important part. I think it's in the later. Okay, so first we can see the NAS architecture background. So NAS has been around since, I think, at least for late 1980s, but it's starting to gain more popular attention until recent years, with people published about NAS with reinforcement learning. And so far, or at least until since 2020, it has been around like 1,000 research papers. So there's a boom of NAS paper. And you can see here we have the bar chart. And I predict it's going to be the same at least in 2023.
Do you think mobile apps and the on-device MLs on the mobile apps has increased the amount of research or interest in this area?
I think it's one of the reasons, because NAS is not just for on-device ML. It can be used elsewhere, like in multiple tasks. But yeah, I think it's the combination of a lot of factors. And right, so as mentioned, we need to define the search space. For example, in this figure, we have search space, which is the most important component of NAS architecture. And also generally it's the first step we do. So what is search space? Because for NAS, when neural architecture search, it's basically we set up a search space of just defined model size, or like different models, different model architectures, and then we do the search. Generally, like the most popular one based on it, we do the random search, which seems very naive, but it actually gives very good results as long as the search space is well defined. And right, so we have the task specific search spaces, and then
So if I have to summarize in just a little bit of layman's terms, is that basically, in order to make it efficient, you have to make it very specific to this use case instead of keeping it generic. That way, you get rid of the redundant or non-relevant spaces or structures. So that way, it's more efficient and only focused on that specific task.
Exactly.
Okay. Thank you.
Yeah, so, and for task specific, I don't really refer to like very model architecture specific, even though it's one of the factors we consider, but it's more about the general model. Like, for example, what is model size? Like, how many layers are in the model? What is model structure? Like, do we have linear layers? Do we have a very specific self-defined model layers? And how those layers communicate? And because generally when we do the search, we do multiple iterations, and in each iteration we have multiple bounds, like lower bound and higher bound. So we need to define those. But the general search rule is always the same. The most popular one, we do the random search. Very, very random, very naive, but it gives you very good results. Right. So because we need to define like search space and search size, like lower bound, higher bound. So we need to be extra careful when we see the size of search space, because if it's too small, it's too string, then it's gonna be faster to find the high performing architecture, but it cannot be used in more broader tasks. And on the other hand, if it's too large with multiple blocks, and it will run longer, but it doesn't actually discover the true normal architecture.
Mhm.
So that's one of the rules we follow when we define the search space. And for search space, there are actually multiple type of search spaces. So this is here just I took the figure from one of the latest NAS summary paper. So I also I think I linked in the slides in the end. So anyone's interested can go to see like how each search space is designed. And for
I just realized. So just help us. Can you, in a very layman's term, define what a search space is?
Search space is basically how are we going to search this model architecture and how the size is defined. So basically, when we do neural architecture search, we put a lot of model sizes of one model into the search space, and then we let it search automatically. So if the NAS works well or is well defined, it will give you the best performing model.
Got it.
Yeah. Okay. And how it's related to on-device ML is sometimes we want to find a smaller model with better performing result. So we can define it using NAS, which is a similar type of network. So we define it so that we have a smaller size model, but it has similar or slightly lower performing rate than the general like baseline model. So that's how we do the NAS search. And here just a few optimization techniques. So we have multiple, we have baselines, RL, evolution, Bayesian, optimization, Monte Carlo tree search, and many, many more. So I'm not going to go to each one, but generally, first one that people always think about is a baseline, which is it's random search. So as I mentioned before, random search is all the architectures are selected very randomly from the search space, and then they're fully trained. Architectures with best validation accuracy is outputted in the end. Right. So before we go into the frameworks, we can say random search is very very naive. Like it's very easy to define. Basically, we just do random searching, but it has like past research have shown that it has given a pretty good results, at least for most like very task-specific tasks. But there are many more optimization techniques made to make NAS work better. And now let's go back to see the on-device AI frameworks. We have TensorLite. So here just I'm listing a few. TensorLite, we have PyTorch mobile, and then MLKate. So this one, the following three are mostly used for design ML models on device. I think mostly it's for mobile development. We have MLKate by Google, Apple Core ML, Embedded Learning Library by Microsoft. This slide is not really updated, so I think some of the frameworks are not really actively maintained by the company, but it's just general understanding to see like we do have some AI frameworks, even though for a lot of models or on-device ML models nowadays, we do it using the general AI frameworks, for example, like PyTorch and TensorFlow, and then we do some very specific tuning or optimization before we ship it to the device. So it doesn't have to be using very specific on-device AI frameworks. As long as we build it and we train it very well, and we can do it and ship it to the mobile devices. And this hyper networks, I would say it's related to NAS. Its general term is almost the same, but it can be used in slightly different way. So hyper networks related to NAS, or at least the rule is related to NAS, it's a neural network that generates the weights of other networks. And we also have a similar one, which is super network, or people always say supernet. It's an over-parameterized architecture that contains all possible architectures in the search space as subnetworks. So you can say the concept is similar to it's the same as NAS. We have all the possible architectures, for example, like model size, model parameter size, like a dimension size, for example, 512, or smaller or larger, 2048. And in those subnetworks, or in all those subnetworks in the search space, we do the search. We either do random search or we follow a really specific rule of the search. Right. So here's all we have so far of efficient model training and inference. And here's just the why do we do the inference? So it's similar as the general goal. We make predictions using a trained model with real-time input on device. And the top reason is if we have security, we have more secure, we have more governance of our own data. We don't have to upload user data to the cloud. Right. So here's the conclusion for the second part of efficient model training, of inference. We talk about distillation, pruning, quantization, and then NAS, neural architecture search, and its related hypernetworks and supernet. Of course, there are many, many more, but those are some of the most popular ones used in research. And here's some learning resources. This is more on the introduction courses. If you are interested, you can go check it out. There's basically give you a general idea of how on-device ML works. And you can always follow the paper released in the recent years. So, okay, so now, let's go to the Q&A.
This is very, very, very helpful, Danny. Thank you so much. This is, I think we all have been talking about the ML and then edge ML, on-device ML. So I have a quick question. So if you go back to the frameworks that are available, have you been able to either try out different frameworks, and is there a specific framework that you suggest, the ones by different companies you mentioned? Yeah, this one.
Yeah, yeah, exactly. That's a good question. Yeah, as I mentioned, I think it doesn't, on-device ML doesn't have to be just related to the on-device ML AI frameworks. For example, like at my daily task, I'm just using PyTorch, because we don't have to follow a very specific on-device AI frameworks to make on-device ML works. Okay. And the general goal is we always wanted to go for more general helpful tools, for example, PyTorch, TensorFlow, JAX, so that it can be very accessible to broader audience, especially if you go to academic research. We are using the same framework. But I'm just mentioning here because some companies are building their own toolkit to build very specific models for devices, because I think there's some security concerns. Like they want to use it for building models on device. Like for example, Apple, they're pretty strict with their security rules, so they use a model kit to build some converters. But if you can see here, it's actually it serves as some very specific purposes. For example, like Apple Core ML is basically just converting PyTorch TensorFlow models using converters. So if you look deep into it, some parts or some components of those toolkits are actually just a part of, they're just using the same one as PyTorch and TensorFlow or whatever general AI frameworks you're using.
Okay, it's more like the base framework is similar, but and then it's been customized for something very specific or a smaller use case or a very specific use case. Interesting. So, which is your preferred one here? Which one do you guys use in your research?
I'm just using PyTorch.
Okay, PyTorch. Yeah. No, yeah, that's so. If you go then to the next part, like you mentioned about pruning, you mentioned about the different different methods to make it efficient. Are there examples where you would use quantization versus pruning versus distillation? Is there specific use cases where you would use one over the other?
We generally try. So the rule is sometimes we don't know which one is better, and there's no general rule to follow. So basically, we're going to try multiple techniques on the same model and to see how the results are, and then we can choose one or we can do one. And sometimes we basically combine all those together. But the general rule is it also depends on how the model architecture is designed, because sometimes quantization, for quantization to work, we need the weights of the model are well distributed, or it's not really well spread out. So if we plot the weights of a model layer, we need to see how nice weights are distributed along the line. And if it's not really well distributed, then quantization doesn't work. So sometimes we just need to see like how model is designed, how weights are distributed. So it's also related to what type of models you're using. And but of course, we can always try first to see how the results are, because it's pretty easy to set up.
Okay, so basically, it's mostly trying. It's basically trial and error. Basically, you're trying to figure out which one works for that specific use case. And then you mentioned a combination. So you basically, there are use cases where you use multiple techniques.
Yeah, but generally is when we do those techniques, there's gonna be a little bit of performance degradation. So it's not going to be the similar level of performance than the dense or the baseline model, but the goal is to make the performance degradation as little as possible. And yeah, it's related to those techniques. How well it works is related to how model architecture is set up, like what kind of weights are, like how distributed or how well distributed model weights are. So it's also related to the model we're using.
Got it. So it's pretty. There's no specific use cases for different techniques.
Yeah.
Let's see. Can you? So there's a question here. Can you also go through one example to clarify the concepts? Or would you be able to provide some basic terminology that we can follow better? Anyone using transformer with NAS? So this is from. So the question is, there are multiple questions here. Is there examples that you can give for quantization? Pruning, and then
examples. Okay. Sorry, go ahead.
Yeah, either the examples or this last question is that is anyone using transformer with NAS?
Okay, thank you. That's a lot of questions.
Yes.
Right, so let me go for the first one. So the first one is, are you going to go through an example to clarify the concepts? Well, I mean, all the things we mentioned so far are just some techniques we use. So it's not just related to one specific example, but I can give you one. For example, if you're using 8-bit of RNNT instead of using the general flow 32 in the training, then there's a little bit of performance duplication in the results. Like for example, ASR. So RNT, we use it for like ASR systems. Then instead of flow 32, now we have in 8. So there's a performance segregation, but because of it, the model is lighter. That's one of the examples. Because like pruning, distillation, quantization, they're all just some techniques we use. So that's the first question. I hope they answered your question. And the second one is, would be one can follow better. I think you can just go to follow the technique slides, because it's just the technique term we use in daily tasks, and it's just same everywhere. If you go online, you search for quantization, you can see people use quantization for their own models. For example, NVIDIA has really nice, they have some pretty nice blogs about how do they do quantization on their own devices, or like how to write the quantization code. And the last, anyone is using transformer with NAS? Yes, of course, because NAS is just a technique we use. So people are going to try with different models. I think one of the similar papers, like 2022, they had a paper of neural architecture search on efficient transformers and beyond. So basically, the author did a lot of they did NAS training with like vanilla transformers, and then they have some very customized transformers. So definitely, yeah, they have some NAS papers with transformers. So I think there's also some with like transformer-based networks. They use transformer-based NAS predictor with a self-evolution framework. I mean, if you go online, you search transformer command with NAS, there are multiple papers popping up, and because there's research in the recent years, so there are going to be more papers of transformer with NAS. Right. I hope this answered your question.
Thank you. No, this really helps. Okay. Bob, can you give one example of 8-bit for video or image? Is YOLO NAS is using quantization or 8-bit?
I mean, I can give you like 8-bit for just for transformers. We have, I think Hugging Face also have a blog on that. So basically, we have like 8-bit matrix multiplication for transformers instead of using FLO32 or other type of data types. As for autos, so I'm not so familiar with auto. I do know like YOLO version 3 and other different type models, but there should be some research on trying like using quantization for different type of image model, because it's basically just a compression technique. People use it everywhere. It's YOLO NAS is using quantization and 8-bit. Okay, so first is YOLO NAS. Basically, we're talking about we're using a YOLO model with NAS architecture. I'm not so sure people have some research on like YOLO combined with NAS search, but there should be one, or even there are not. It's basically just we can treat it as an image recognition model combined with NAS architecture. We can use it together definitely. So we can use quantization plus neural architecture search, or we can just using quantization or just neural architecture search. But sometimes people do multiple to make the model much smaller. We do really extreme compression techniques to make smaller lightweight models so they can run on actual devices. So it's possible we do it together. But sorry, I don't have more information on YOLO because I haven't used CV model for a long time.
That's okay, no problem. Thank you so much, though. Thanks, Bob, for your questions.
Yeah, that's a good question.
Thank you. No, this is really good. So I'm going to stop YouTube Live right now. So anyone who's joined on YouTube, thank you so much for joining us. And we will forward you the slides if you have registered from Dani. And Dani, thank you so much for being with us and helping us walk through this this topic. So thank you. See you.